This is the second video on linear programming. In this video, we will learn about the different terms that are used in linear programming. That is the objective function, feasible region, constraints, feasible solution, and optimal feasible solution. Let us continue our earlier example to understand these terms here. So the example was a furniture dealer deals in only two items, tables and chairs. He has $50,000 to invest and has a storage space of at most 60 pieces. He can store up to 60 pieces. A table costs him $2,500 and a chair costs him $500. Okay, he estimates that from the sale of one table he can make a profit of $250, and from the sale of one chair he can make a profit of $75. He wants to know how many tables and chairs he should buy so as to maximize profit. Okay, so the endeavor of this dealer is to maximize profit here. Okay, now first thing is we will see how to construct the constraints here. Okay, so by constraints what we mean, the linear inequalities or equations or restrictions on the variables of a linear programming are called the constraints. Okay, so we are being told he has total $50,000 to invest. Okay, or let me write it here. Let's write it here, $50,000. $50,000, and this $50,000 has to be invested on tables and chairs. Okay, let x denote the number of tables and y denote the number of chairs. Okay, so that means x plus y. Okay, so x denotes the number of tables and y denote the number of chairs, and we are being told a table costs him $2,500. That means we have 2,500 into x. That means total investment on the tables will be equal to 2,500 times the number of tables bought, plus the investment on the chairs will be equal to the number of chairs times the cost of one chair, that is being told us as 500. So we can write it here 500. Okay, so 2,500x plus 500y, and it should be less or equal to the total investment that this dealer wants to invest. Okay, so a total investment on these two items should be less or equal to 50,000. We call this the constraint, and this is our investment constraint. Also, we are being told that he has a storage space of at most 60 pieces. He can store only 60 pieces. So that means again x, that means number of tables plus number of chairs, and let's denote it by y. It should be less or equal to 60. Okay, this is the storage constraint, this is the investment constraint. Now this what we call this dealer, we are also being told that he estimates that from the sale of one table he can make a profit of $250, and from the sale of one chair he can make a profit of $75. And here this denotes our objective function, and let me be very specific, let's denote it by z. That is the profit function here, what we call the objective function. So what will be the profit for this dealer? That is equal to x plus y, and let me write it here y. So profit that he will get from the sale of one table is 250. So total profit will be equal to 250 times the number of tables sold plus the profit on one unit of chair, that is 75 unit. Okay, so this is our objective function. What is the objective function? And let us see the definition here. Objective function is a linear function that is in the form of z is equal to ax plus by. A and b are the constants. Here we have 250 and 75 in place of a and b, which has to be maximized. We want to maximize this function, that is we want to maximize the profit function. profit. Okay, let me write it here. We want to maximize this objective function. Okay, here x and y are called the decision variables, the variables on which our profit will decide. They will decide basically how much profit will this dealer get. These are called the decision variables or choice variables. So this is our objective function, a linear function in the form of z is equal to ax plus by, where a and b are the constants which has to be maximized or minimized. In this case we want to maximize profit. At any other instance we would have to minimize the cost. Okay, so since this is the maximization, the dealer wants to maximize profit, so this is the maximization problem. Okay, now this is called, these two are called the constraints. And what are the constraints? These are the linear inequalities. Okay, so we have here inequality signs or equations or restrictions on the variables. So the restrictions on the variables, these are actually our linear inequalities, and these are called the constraints. We have here two constraints. Okay, in addition to this we have two other constraints, that is x should be greater or equal to 0. That means number of tables should be greater or equal to 0. They obviously tables cannot be negative, or the chairs that are bought cannot be negative, and also y should be greater or equal to 0. Okay, so when we formulate this function in this form, now we want to find out the solution of this very function. Okay, so objective function, we know what is this. Constraints, we also know we have two constraints, that's total investment on x and y should be less or equal to $50,000, and we have also the storage constraint. That means total number of items that he can store should be less or equal to 60. The dealer wants to maximize the profit from selling tables and chairs, and he faces these four constraints here. Okay, so how do we solve this now? Let's try to find out. Okay, and let me put it here for the time being. So what will we do to solve this this problem? First thing is we will form the graph here, or we will draw the graph here, and let me be very specific here. We have the number of tables on the horizontal axis and number of chairs on the vertical axis. First we will try to solve these constraints here. Let's take this first constraint, that is the investment constraint. So we have 2500 x plus 500 y. It should, and we replace this with the equality sign here, so that we can draw it on the so that we can find out the intercepts here is equal to $50,000 here. Okay, so here we can do one thing. If we divide both sides by 100, so these two zeros will get cancelled, and here these two zeros will get cancelled. I hope I am making myself clear here. We have 2500, 500 and 50,000 here. So what we will get here, we get 25x plus 5y is equal to 500. Again we can simplify it. If we divide both sides by 5, so we will get a 5x plus y should be equal to 100 here. Okay, so we want to draw this very equation on the graph. Okay, how do we solve this very thing here? So first thing is we put x is equal to 0. If x is 0 in this equation, that implies y will be equal to 100. Second, we put y is equal to 0 in this equation, then x will be equal to 100 upon 5, which is 20. So x will be equal to 20. So what are the pointers here? So x is equal to 20, y is equal to 0. Let's say this is here 20 and y is 100. Let us say 100 is here. Then we join these. Okay. So this is the graph of the first equation. 2500x plus 500y is less or equal to $50,000. And let us rub this out. Similarly, we will try to find out this very line here. Okay, rather graph this very line. So x plus y is equal to 60. That means when x is equal to 0, when x is equal to 0, y will be equal to 60. And when y is equal to 0, in this equation, x will be equal to 60. Okay, so another line will be 60 and 60. And let's draw it here. So let us say this denotes 60 and this point also denotes 60. And let's join them. So here we have 60. Here we have also 60. X greater or equal to 0, y greater or equal to 0. So we are being restricted in the first quadrant. Both the x and y should be greater or equal to 0. So this is our origin here. Now the thing is, what is the feasible region? The common region determined by all the constraints, including non-negative constraints of a linear programming, is called the feasible region. Okay, so the common region that is being decided by these two curves will be called the feasible region. And here you can see what is the feasible region. And let's see, since we have this less or equal to sign here, that means feasible region will be this very region, that is common region between these two lines. Okay, so our solution, and let me be specific, our optimal feasible solution will lie in this region. Okay, so first we draw this very line, then we draw this very line, then we have the feasible region. The common region determined by these two regions is called the feasible region. After that, we need to find out the feasible solution for this problem. Okay, so by feasible solution, what we mean, points within and on the boundary of the feasible region represent the feasible solution of the constraint. The point is, suppose this is the point, and we have this point and this point and this point. These points and the area that is shaded is called the feasible region. We know this point, we also know this point, but we don't know this point. So for this, we need to solve these two equations. So we have 5x plus y. When we solved it earlier, simplified, it was equal to 100, and this x plus y was equal to 16. We need to solve these two equations so as to get this very point. Okay, so how do we solve this? By substitution method. Let us solve the second equation first. That means x is equal to, transposing this, it will become 60 minus y. We plug the value of x is equal to 60 minus y in this equation, that is 5 in place of x we have 60 minus y, so I will write 60 minus y plus y should be equal to 100, which gives us 5 6 are 300, which implies 300 minus 5y plus y should be equal to 100. If I or it will become 300 minus 4y is equal to 100, or 4y will be equal, transposing this, it will become 200, or y will be equal to 200 upon 4, 200 upon 4, which gives us 50, I guess. No, 4 5s are, am I doing it correctly or not? Let me be. So x plus y is equal to 60, so 5 6s are 300, then we have 5y minus 5y plus 4y is equal to 100. So 300 minus 4y is equal to 100, which implies, transposing this here, it will become 200. So we have here 50. Okay, I guess I'm doing 4 ones are 4, 4 5s are 20, so we get x is 50, and let me write it here. We have 50, the value of x, and to find out the value of y, simply plug y is equal to 50 in this equation. So x is 50, so we have 50 plus y is equal to 60, or y will be equal to 60 minus 50, which is equal to 10. So the value of y will be equal to 10. Okay, so it is very simple. I'm just dragging this for the sake of understanding. Simple thing is, we want to solve these two equations to get the values of x and y, and we got the values of x and y is 50 and 10. Okay, now we are being told what is feasible solution. The feasible solution will be the points within and on the boundary of the feasible region. Okay, so our feasible solution are all these points within and on the border of the common region of these two lines. Okay, simple thing. Now next thing is optimal feasible solution. We want to find out the optimal feasible solution. So optimal feasible solution is any point in the feasible region that gives the optimal value or maximum value or minimum value of objective function. Okay, so optimal feasible solution is that very solution, uh, rather optimal solution is a point, any point in the feasible region. This is the feasible region when we evaluate our objective function at these points. Okay, we then want to see which of these points will maximize this objective function, and that very point will be our optimal solution. Okay, and let us see here what exactly is meant by this. So our objective, our endeavor is to maximize profit. Okay, so we let us say this is point A, this is point O, this is point B, this is point C. Okay, we want to evaluate our profit function at each of these points so as to find out which at which point our profit is maximized, because this is the maximization problem here. Okay, so any point in the feasible region that gives us the optimal value, in this case the maximum value of this objective function will be our optimal feasible solution that we are supposed to find out. So we have points A, or let me write here point O first, point O, A, B and C. Okay, and we at point O we have the value of x and y will be 0 and 0. At point B the value is what is at at A we have x is 0, y is 60. At point B both we have 50, the value of x, and 10, the value of y. And at point C we have 20, the value of x, and 0, the value of y. Okay, we want to evaluate our profit function, that is z is equal to 250 into x plus 75 times y. Okay, we evaluate our function at different points. When x is equal to 0, y is equal to 0, our z will be here equal to 250 times 0 plus 75 times 0, which will be equal to 0, obviously. Then we evaluate this objective function at point when x is equal to 0, y is equal to 60. Then what will be the profit? Let us see here. Z will be equal to 250, the value of x, which is 0, plus 60 times the value of y, which is 60 here. Okay, so 250 into 0 is 0, 60 into 6 is 36 here, 60 into 60 is 3600. So at this point, total profit that the dealer will get is 3600 if he only produces chairs, and he produces 0 units of tables, rather sells or whatever he is doing here. Now we want to evaluate this profit function at a point B. when x is equal to 50, y is equal to 10. So we have 250, the profit for each year, rather the profit for each table times the units of table, which is 50, plus then we have 75 into y, the value of y is 10. And let us solve this. So we have two zeros first, then we have 5 5s are 25, then we have 5 2s are 10, 11, 12. So $12,500 of profit he will make at this point. Okay, now let's evaluate at point C. So Z will be equal to 250, the units of x, that is 20, plus 75 times the units of chairs, sorry, okay, it is correct, it is chairs, y denotes the chair. So what is the profit here? So we have two zeros first, then 2 5s are 10, 2 2s are 4, which is 5,000. Okay, 5 5s are, so we have two zeros here first, 5 5s are 25, then 5 2s are 10, 11, 12. Okay, so I hope I have done the calculation right here. Okay, now what is our optimal feasible solution? I have told you any point in the feasible region that gives us the optimal value. Our optimal value will be the maximum value here. So when we evaluated our objective function at different points, that very point which gives us the maximum value of objective function will be our optimal feasible point. So I guess this very step gives us the optimal feasible solution. So the solution for this manufacturer, rather this furniture dealer, is that he should produce 50, rather he should buy 50 chairs, sorry, tables, and y is equal to 10 chairs, so as to maximize his profit. Okay, so I hope I make myself clear in this video. First, we to solve the linear programming problem graphically, first we need to formulate the problem. We want to formulate our objective function. Okay, by objective function we mean a linear function in the form of z is equal to ax plus by, where a and b are the constants which has to be maximized. This x and y are the decision variables or choice variables. Okay, then when we formulate our objective function, then we formulate or construct the constraints. And here the constraints were simple thing, that is this manufacturer dealer had total $50,000 to invest on, tables and chairs. Okay, so total investment on chairs and tables should be less or equal to $50,000. And this storage, or rather this furniture dealer also faced a storage constraint. He could only store 60 pieces, so total number of tables plus chairs should be less or equal to 60. Then what we do, we draw the graph of these inequalities on the graph here. Okay, then we also formulate these non-negative restrictions, because units cannot be negative here. Then we evaluate the profit function at different points, at this point, this point, this point, and this point. Then we see which of these points gives us the maximum value, that means where our profit function is maximized, and the point that maximizes the profit function will be our optimal feasible solution. Okay, so I hope I make myself clear in this video. Thank you.